So let me write the theorem. So let P be a P group of order P power A, where P is a prime number. Then P is nilpotent with nilpotency class at most A minus 1, and this happens for A greater than 2. For A equals 0 and 1, nilpotency classes A itself. Okay, so so proof. So first let us finish the case of A equals 0 and A equals 1. Okay, so let A equals 0. If A is 0, then what is the order of P? Order of P is P power 0, which is 1. Okay, and hence the group is nothing but the identity group, right? And then Z naught P is by definition the identity element, and which is the group itself. So this will imply P is nilpotent with nilpotency class 0. So for A equal to 0, it is nilpotency class is A itself, right? Now let A equals 1. Okay, then what is order of P? Order of P is P power 1, which is P. Uh, Hence, P is nothing but the group ZP. Okay,
Exactly.
and ZP is abelian, which is abelian. So therefore, the upper central series will be upper central series will be Z naught of P, which is always identity, and then Z1 of P, which is just P, right? So, and it will stop there. So this will imply P is nilpotent with nilpotency
Class.
class 1, which is A, right? And in this case also it was A.
Okay.
So the cases which is A is 0 and 1 is over. Okay, those are the easy ones. Okay, so now let A is more than equal to 2. Hmm? Okay, so let's try to understand. So we have P is a P is a P group. Okay, order of P is P power A. Now we also know that P groups have non-trivial center. So any P group has non-trivial center. Okay. Uh, so what does it mean? That is Z of P is actually not equal to E. Okay. Now this group, the quotient groups P mod ZIP are also P groups, right? See, because P's order is P power A, P's order also will be P power something, right? Because the order of ZP, what is the reason? Because order of ZIP divides order of P, right? So this is also a P group. So what does it mean? Therefore, center of uh, P mod quotient ZIP is not equal to identity. But what is the identity element here in this? What is the identity element in P mod ZIP? It is ZIP quotient ZIP, right? So what does it mean? This means, let me write it again. That is, this ZIP quotient ZIP is a proper subgroup of Z of is a proper subgroup of the quotient of P quotient ZIP, which is nothing but ZI plus 1P modulo ZIP. So what is the upshot of this? The upshot of this is that uh, ZIP is properly contained in ZI plus 1P. That is, ZI plus 1P is strictly bigger than ZIP. Okay? Is this fine? Okay. So, therefore, what will be the order of ZI plus 1P? It has to be strictly bigger than order of ZIP, but it has to be bigger than equal to a multiple of P. Is this part clear?
I didn't understand, sir.
Yeah, see, let's think like this. Let's say order of P is P power 10, right? Correct? And let's take a particular number. Let's say 3 power 10, okay? And now you have ZIP, which is a proper subgroup of ZI plus 1 P, okay? Now what is the possible order of ZIP? ZIP's order is also 3 power something,
Yes.
correct? And Zi plus 1p's order is also 3 power something,
Yes.
isn't it? Right? But this is bigger than this strictly,
Yes, sir.
isn't it? So what I'm saying is, if, for example, if this is 3 power 6, this has to be at least 3 power 7, right?
Mm.
Isn't it? Otherwise, how will it be bigger? So that means this the order of, that means, and what is, it can be 3 power 7 or 3 power 8 or 3 power 9 or 3 power 10, right? But
Yes.
at least it will get multiplied by 3, right?
Okay.
So
Yes.
the order of Zi plus 1p will be at least p times Zip's order. Okay?
Okay, sir.
Okay. So in particular, let's in particular, if I put I equals 0, what do I get? For I equals 0, uh,
One of P
I will get Z1 of P is more
is
than
great.
equal to P into Z naught
Z
of
not of
P. But what is Z naught of P is identity, right? So this is just 1. So this is greater than P. Now if I do for I equals 1, what will I get? Z2 of P is greater than, P into Z1 of
Z.
P. But Z1 of P is further greater than P. So P dot P, which is P square.
Then
Okay. So recursively we get, so by the time I come to ZA of P, what will I get? It should be greater than equal to, so not greater than equal to, okay, it has to be greater than equal to, okay, greater than equal
P.
to P power A, right? What does that imply? ZA of P is greater than P power A. Can you say what does it imply? See, the whole group's order is P power A, okay, and you have a subgroup which whose order is bigger than equal to P power A. So what should be that subgroup? See, you have a group which is P power A, and inside that you have got a subgroup whose order is more than equal to P power A. So what should be that subgroup?
More than P. What subgroup?
the group itself.
The group itself, right? So ZA of P is P. What does it imply if ZA of, sorry, I mean, yeah, correct, ZA of P is P. So what does it imply? This will imply P is nilpotent. What was the definition of nilpotent? That there is some C such that ZC of G is G, right? So this will imply P is nilpotent, and with nilpotency class,
A.
no, we can't say A. We can only say that at most A, less than or equal to A.
Okay.
Because ZA of P is P, it might happen that Z of something lesser than A of P is also P, right?
Okay,
Correct?
sir.
With nilpotency
Yes.
class, at most A. So we are almost done. What we had to prove? We had to prove that it's nilpotent and the nilpotency class is at most A minus 1. But till now what we have shown, the nilpotency class is at most A.
At
So what
most
is left
A.
out to show? Hence, it is, so what is left out to show? Can someone tell me? It is left out to show that the nilpotency class of P cannot be what? Cannot be A.
A.
Yeah, good. Okay. So we will show this now. Okay. So we show this by method of contradiction. So what do we say? We say if possible, let nilpotency class of P be A. What will that imply? That will imply that ZA of P is P, and also Zi of P is not equal to P for I less than A. Okay. In other words, that is A is the smallest integer such that ZA of P is P. Okay, so we have this now. Somehow we need to get a contradiction. Okay, let's see. So uh, see the uh, ZA of P is P will imply that the upper central series is uh, Z naught P, uh, Z1P, Z2P, till what it will go? Till
Zero.
ZA of P, which is P. After that, it will just keep repeating. It will be P, 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 P. Okay. See, also none of this inequalities or containment can be actually equal, right? Because if two of them are equal here, suppose Z3P is Z4P, what did we see? Then Z5P, Z6P, all of them will become same, right?
P.
And that will contradict that ZAP is P.
Yes.
Okay, so let's also write it down here. See, also uh, none of the inclusions are equal in the chain uh, else the chain would have stabilized at that point and will contradict minimality of A. Okay, so none of these are equal. Okay, so let me write it down here, the chain again properly, and the proof is almost done. Okay, so let's see. So Z naught P is not equal to Z1P is not equal to Z2P, and then there is Z of A minus 1P is, and then there is ZAP, which is P. Okay, so we have this. Also, can you tell me what are the orders of each of this? What is the order of this? What is the 1? So this is P power 0. And what is the order of this? This is P. So this order is P power A, right? What are the possible orders of the, rest of it? See, and what are the possible orders of this? Now, at least we know it will be P power something, right? All these orders are P power something, right? Now, can this be P power 2? Suppose this is P power 2, then this has to be at least P power 3, the next one, correct? At least it has to increase by 1. Then by the time you come here, it will become P power A. See, if you start with 2 here itself, then by the time you see at 1, if we start with 2, by the time we
Yes,
come
yes.
A minus 1, it will become A. But you have said that ZA of P is P power A and none of the previous ones are P, right? Which will be a contradiction, isn't it? So if you want to have Z A is the smallest such, you have to have all these orders are what exactly? This is P power 1, this is P power 2, and this is P power A minus 1. Okay, there is no other choice. So let's write down that also such a chain is possible when each Zi of P's order is actually Pi for I equals 0, 1, 2, A. Okay, very good. Now, uh, in particular, what is the order of Z of A minus 2 of P? It is P power A minus 2. So, yeah. So what will be the, consider the quotient group. Consider the quotient group P mod Z of uh, P mod Z of A minus 2 of P. Okay. Is of order. What will be its order? It will be order of P by order of Z of A minus 2 of P. So this is P power A, this is P power A minus 2, and this is P square, right? Okay.
Yes, sir.
So what will that imply? That will imply that this P mod Z of A minus 2P is isomorphic to either ZP square or ZP cross ZP. Any group of order P square is one of this. Okay. Both of which are abelian. So if I take Z of P quotient Z of A minus 2 of P, what should be center of this group? This is a abelian group. So what should be the center?
P by Z minus 2.
Very good. P by Z of A minus 2 of P. That means this is my Z of A minus 1P. That is how you get Z of A minus 1P recursively, right? You take P by Z of A minus 2P, take the center of it, and you see what you what do you get as the numerator in the quotient, right? But which is a contradiction? Which is a contradiction to the minimality of A. So we are done. So we have what we have proved. Therefore, the nilpotency
Is not equal to A.
yeah, class of P cannot be A. Okay, we are done. That is what we said is left to prove right here. Hence, it is enough to show that nilpotency class of A cannot be A, because nilpotency class of P cannot be A. That means it has to be less than equal to P minus 1, which was what was the theorem. So are we done? The proof is over, right? Okay. So we will end here for today's class. We'll meet again in
Yes.
the next class.
Yes, sir.
Okay, so let me save the whiteboard and let me